Hi everyone. Until now, we learned how to design algorithm. From now, we'll walk through the performance analysis of the algorithm. Our goal is to compare the performance of algorithm to find the most efficient one. So here, we focus on asymptotic analysis to understand how the algorithm behave as the input size increases. This would be helpful to evaluate the performance of algorithm. To begin the analysis, we first need to define the problem clearly. So now I want to introduce one of fundamental computer science problem called sorting. When we define a problem, we describe the input and the output. The input is a sequence of number in sorting problem written as A1, A2, and so on up to AN. The output is a permutation of A1 prime, A2 prime, and AN prime, where the numbers are in non-increasing order. For example, one input instance is 8, 2, 4, 9, 3, 6. In this case, sorting algorithm should produce the following output: 2, 3, 4, 6, 8, 9. The goal of algorithm is to design an algorithm that performs this process efficiently. Now that we have defined the sorting problem, let's discuss why this problem is so important. Sorting is used in many clear applications, such as organizing an MP3 library or maintaining a list of student records. It also helps solve certain problems more easily once the data is in sorted order. For example, we can quickly find the closest pairs, and also we can perform binary search based on the sorted list, and also sometimes we can also detect the statistical outlier based on sorting result. Even in less obvious areas like data compression, where we search for duplicate, or in computer graphic, where scenes are landed from front to back, sorting still plays an important role. Okay, so probably most of you already understand the sorting problem. Here, we want to introduce an algorithm to solve this problem. Our first algorithm is called insertion sort. This is a simple and intuitive sorting algorithm. Our main idea is to build on existing sorted list. Given a sorted sequence, we insert a new element into the correct position so that the list remains sorted. For example, if we have the list 2, 4, 5, 10 and we insert 7, it goes between 5 and 10, resulting in 2, 4, 5, 7, and 10. Basically, given a sorted list sequence, we want to insert a new element. So as I already explained, given 2, 4, 5, and 10, when you want to insert new element 7, in this case, 7 should be located between 5 and 10. So the resulting sorted list should become 2, 4, 5, 7, and 10. This is the basic procedure of insertion sort. Okay, let's see how this algorithm works step by step. We start with a sorted list 2, 4, 5, and 10. This is very important. We assume our list is already sorted. Now we want to insert new element 7. First, we compare 7 with the last element, which is 10. Since 10 is larger than 7, we shift 10 one position to the right. Okay, so 7 should be located before 10. Next, we compare 7 with 5. Since 7 is larger than 5, we have found the correct spot. 7 should be located after 5. So we insert 7 in between 5 and 10. So the final result is like this: 2, 4, 5, 7, and 10. Okay, now I want to explain the code for the insertion step. This code inserts a new element into the sorted part of the array from index 0 to I minus 1. We start by declaring the integer variable j, then we use a for loop to move from right to left, starting at position I minus 1. While the new element t is smaller than aj, we shift aj one position to the right. We keep doing this until we find an element that is smaller than or equal to t. At that point, we stop the loop and insert t at position j plus 1. Now we can build the full insertion sort algorithm based on the insertion step. We begin with the first element, which is already sorted by itself. This is very important. If we have just only one element, this is also a sorted list. Okay? So our assumption is still maintained. So we can begin with this one single element which is already sorted by itself. Then we go through the rest of the element one by one and insert it into the correct position in the sorted part of the array A. Okay, so you can see this pink part indicate insertion procedure. Okay, when we design algorithm, sometimes we need to reuse existing module. So we first design the insertion part, and then we can just reuse this module for the full insertion sort algorithm. This way, the sorted portion grows step by step until the entire array is sorted. Let's look at an example of insertion sort. We start with the first element 8. It is already considered sorted, as I already explained. Now we insert the next element 2 into the sorted part. We'll continue this process for the rest of the element 4, 9, 3, and 6. We insert 2 into the sorted part, which currently contain only 8. That is, we compare 2 with 8. Since 2 is smaller, we move 8 to the right and place 2 before it. After inserting 2, the next element is 4. We compare 4 with the sorted part, which are 2 and 8. 4 is greater than 2 but less than 8. So we shift 8 to the right and insert 4 in the middle. Now the sorted list become 2, 4, 8. Okay? The sorted list grows one by one. Now we have a sorted list 2, 4, 8. The next element to insert is 9. We compare 9 with 8. Since 9 is larger, it stays in its place. Basically, only one comparison operation is sufficient to finalize this step. So the sorted list becomes 2, 4, 8, and 9. The next element is 3. We compare 3 against 9, 8, and 4. And also, we know that all of them are larger than 3. So they are shifted one step to the right. Now, the sorted list becomes 2, 3, 4, 8, and 9. The next element is 6. We compare 6 with 9 and 8 sequentially, and they are larger than 6, so we shift them to the right. Then we insert 6 after 4 because 6 is larger than 4. So the updated sorted list is 2, 3, 4, 6, 8, 9. And there is no remaining element to insert. So the insertion sort process is complete. As we can see, this algorithm correctly placed each element into its proper position step by step. Next, we'll analyze how efficiently this algorithm performs depending on the size of the input. Okay, until now, I just explained how this algorithm works, but we don't know how much this algorithm is efficient. So I will explain how to evaluate the performance of this algorithm. Okay, the performance of an algorithm depends on the input. For example, insertion sort runs much faster on an already sorted list than on a random one. To measure efficiency, we look at the running time in terms of input size. Maybe we need to consider all possible input cases, but it is practically a challenging task. To simplify this process, we use a simplified convention. Let T sub A n of n be the time it takes for algorithm A to process an input of size n. Okay, we define this function to measure the time of algorithm on length n input. In most cases, we focus on finding an upper bound for this running time, so we can guarantee performance no matter what the input looks like. Okay, definitely there are so many input of length n, so maybe depending on input, the performance and running time can be changed. To simplify this process, we usually just focus on upper bound on the running time of the algorithm. Okay, as I mentioned, we focus on the upper bound of running time. But generally, we can consider the following three cases. First, the worst case. This explains the upper bound of running time. This tells us the maximum time the algorithm can take for any input of size n. It is most common kind of analysis because it gives us a reliable upper bound. Second case is the analysis of average case. This shows the expected running time over all possible input, but it requires assumption about how the inputs are distributed, which can make it harder to calculate. We need to have the assumption of input distribution. Lastly, the third is the best case. This shows how fast the algorithm can be on the earliest input, but we usually ignore it since an algorithm that works well only in the best case can still perform poorly most of the time. So usually we do not consider this best case. When we talk about running time, we want to focus on the algorithm itself, not the machine it runs on. This is very straightforward. Different machines can give different execution time, so we ignore machine-specific constant. Instead, we look at how the running time grows as the input size increases. We write this as T of n as n goes to infinity. This is called asymptotic analysis. It helps us compare algorithms in a machine-independent way. Okay? Maybe you use a 32-bit machine, and maybe I use more advanced, powerful server. In this case, maybe when we run same algorithm, in this case, maybe running time could be greatly different. Okay, so we want to ignore this kind of machine-specific constant. Okay, so in this case, we can purely focus on algorithm itself. Okay, so we use asymptotic analysis when n goes to infinite. This time complex function Tn goes to some specific pattern. Okay, so some of you already heard about big O notation, which is one of asymptotic analysis. Big O n squared, big O n cubed, or something like that. In asymptotic analysis, we focus only on the important part of an algorithm running time. We ignore constant and low order terms because they become insignificant as the input size grows. This helps us compare algorithm in a machine-independent way and also more easily, focusing on how the running time increases as input size n becomes large. Let's take a look at the three expressions on the slide. The first one is 16n cubed plus 20n plus 16. The second one also starts with 6n cubed, but plus a term with n to the 4/3 and a constant 56. The third one includes the same 16n cubed minus 1/2 n squared and plus 1/3 n. At first glance, these all look different, okay? But as n becomes very large, such as 1 million and 10 million or 1 billion, in this case, the low order terms like n squared or just linear n or n to the 4/3 or constant becomes negligible. Okay, so eventually all three behaves like 1, 6, and cubed. Look at this graph on the slide. Okay, the low terms and constant only make small difference even when n is around 10. Okay, so in asymptotic analysis, we approximate all of them as just 16 and cubed. This is how we simplify complex expression and focus on the dominant growth, which we capture using big O notation. By focusing only on dominant term, we can classify algorithms by their order of growth. And here is good news. We only need to remember a small number of common patterns like this: 1 log n log n squared, n cubed, and 2 power 2n. Okay, we can consider only small set of asymptotic function. Okay, you can see this graph shows how fast each of these grows as the input size increases. This classification helps us quickly compare algorithms and understand which ones scale better with large input. Usually in our algorithm course, we'll focus on designing algorithm below quadratic time. Okay, I want to explain why this asymptotic analysis is very important by comparing big O n squared against big O n cubed. When n becomes large, an algorithm with learning time big O n squared will always outperform one with big O n cubed. The graph shows that even if the big O n cubed algorithm starts faster for small input, it grows much faster and eventually becomes slower. This is why asymptotic analysis is so useful. And also, it helps us reason about performance in the long run and choose algorithms and scale better with large input sizes. When we do asymptotic analysis, we often use three common notation: big theta, big O, and big omega. They are from Greek alphabet. Big O describes an upper bound on the running time. Okay? Big theta gives both an upper bound and a lower bound. Big omega gives a lower bound, showing the best performance we can expect. These are not just single function, they are set of functions. For example, big theta of n squared include all functions where the highest order term is n squared, such as 1/2 n squared, 10n squared, or 5n squared plus 22 n log n. Okay? It indicates a set of functions. Similarly, big O of n squared include everything in big theta of n squared plus small one like linear or log linear terms. Big omega of n squared also include big theta, but also larger function like n to the fifth. So to prove that a function belongs to big theta of some expression, we must show that it fits both big O and big omega of the same expression. Let's look at our first asymptotic notation big O. We write it using a capital O. As I already mentioned, it is derived from Greek alphabet. We say Fn is in big O of Gn if and only if there exists positive constant C and N0 such that Fn is less than or equal to C multiply Gn for all n, where n is greater than or equal to N0. Basically, this big O notation gives us an upper bound of function Fn. As shown in the graph, beyond N0, Fn never grows faster than a constant multiple of Gn. Here is an example to apply the definition of big O. We have Fn equals 25 times n and Gn equals 1/3 times n squared. We want to show that 25n is in big O of n squared over 3. Let's choose the constant C as 1 and check the value. At n equals 1 or 2, Fn is greater than Gn. But when n equals 75, both are equal, 1875. From that point on, Gn becomes larger than Fn. Actually, from 75, n equals 75, Gn is always greater than or equal to Fn. It means that Fn is less than or equal to C times Gn. This confirms that Fn is in big O of Gn. So this indicates that Gn is an upper bound of Fn. Okay, what does it really mean when we say Fn is in big O of Gn? It means that Gn gives an upper bound on the growth of Fn for all n beyond some point N0. But you should keep in mind big O only tells us that Gn is a valid upper bound. It does not tell us whether it is a good or tight upper bound. For example, if Fn equals n, we can say Fn is in big O n squared, or even big O 2 to the power n, which is obvious to lose. That is why big O 2 power n is sometimes called a cheat key for upper bound problem. It's always true, but not useful. So in practice, we try to find the smallest possible Gn such that Fn is less than or equal to C times Gn. That gives us the tightest upper bound. Okay? We want to find smallest possible Gn, tight upper bound, rather than loose upper bound such as 2 to the power, 2 power to n. Also, please remember that Fn equal big O Gn does not mean Gn equal big O Fn. Big O is not symmetric. Okay, we are now looking at an important theorem in asymptotic analysis. Theorem is like this. If Fn equal ak multiply n power k plus a1 multiply n plus a0, then if we Fn, when Fn is this kind of expression, in this case, Fn equal big O n power k. This means that for any polynomial, the growth rate is determined by the highest degree term. Until now, I explained we can, in asymptotic analysis, we can just focus on the highest degree term. We can ignore constant and load term. Actually, this theorem supports this property. Okay? We can only consider highest degree term. Let's look at why this is true. We take the absolute value of each term and factor out n power k. The rest becomes a constant when n is large enough. So the whole function is bounded by c times n power k for some constant c. That's why we say only the highest order term matter. Okay? This is just constant. Okay? So we can just consider highest degree term only in asymptotic analysis. Okay, we now go through a few examples to practice big O notation. First, let's show that 2 multiply n squared is in big O n cubed. Basically, we want to prove 2 multiply n squared is less than or equal to c multiply n cubed. In this case, if we just divide both sides by n, in this case, we get 2 is less than or equal to c multiply n. And also this is true when we set c equal 1 and n0 equal 2. Okay, so we know that 2 n squared is in big O n cubed. Now let's show n squared is in big O n squared. In the same way, we need to check if n squared is less than or equal to c multiply n squared. Okay, so we divide both sides by n squared. So 1 is less than or equal to c. Okay, so we can also show this is true when it said c equal 1 and n0 equal 1. Okay, and then we want to show 1000 n squared plus 1000 n is in big O n cubed. In this case, this equation is less than or equal to 1000 n squared plus n squared. So in this case, we can calculate the right side. So we can get 1001 multiply n squared. So when it's set c equal 1001 and n0 equal 1000, in this case, this equation is satisfied. Okay? Okay, this is our final example. We wanted to show n is in big O n cubed. Basically, we want to show n is less than or equal to c multiply n squared. So we divide both sides by n. So 1 is less than or equal to c multiply n. So we know that this is true when it's set c equal 1 and n0 equal 1. These examples show how to find constant c and n0 to verify a big O relationship. Okay, basically, to prove such expression, you need to find constant c and n0 to satisfy this expression, this inequality expression. Okay, we often talk about finding constant c and n0 when proving a big O notation. But you need to keep in mind these values are not unique. Let's prove that 100 multiply n plus 5 is in big O n cubed. We can show 100 multiply n plus 5 is less than or equal to 100 multiply n plus n, because 101 multiply n is less than or equal to 101 multiply n squared. For all n is greater than or equal to 5. In this case, we can get n0 equal 5 and c equal 101. This is one possible combination of n0 and c1 to prove this expression. Okay, but we can also obtain different combination of n0 and c. 100 multiply n plus 5 is less than or equal to 100 multiply n plus 5 multiply n. Okay, so for all n is greater than or equal to 1, 105n is less than or equal to 105 n cubed, n squared. Okay, so in this case, n0 equal 1 and c equal 105. This is a possible solution. Okay, so we know that there is no unique combination of n0 and c1, but to prove a big O expression, you can find some constant c and n0 that satisfy the asymptotic notation relation. Just one pair of n0 and c is sufficient. Okay, we now introduce another asymptotic notation, big omega. We also similarly use the Greek letter big omega to represent it. We say that fn equal big omega of gn if and only if there exists positive constant c and n0 such that fn is greater than or equal to c multiply gn for all n where n is greater than or equal to n0. This means that the Gn is a low bound on the growth of Fn for all n where n is greater than or equal to n0. Okay, so from the point n0, Gn is always less than or equal to the function Fn. Okay. And just like before, we want to get Gn to be as large a function of n as possible. We also have a similar theorem. If Fn equal ak multiply n power k plus a1 multiply n plus a0, and all coefficient am is greater than 0, then Fn is big omega of n power k. Okay? In this case, we satisfy this condition. Our expression satisfies this condition. In this case, we can also consider the high degree term to measure big omega. Okay, we can now compare big O and big omega using this graph. Visually, I can explain the difference between big O and big omega. We see that big O gives asymptotic upper bound of the function Fn. Okay, the function Fn stays below C multiply Gn after some point n0. On the right figure, big omega gives low bound. The function Fn stays above C multiply Gn from some point n0. In both cases, Gn acts as a bounding function, either from above or below, depending on the notation. Now, I would like to introduce our last asymptotic notation, big zeta. We use the Greek capital letter zeta to describe this notation. We say Fn equals big zeta of Gn if and only if there exists positive constant C1, C2, and N0 such that C1 multiply Gn is less than or equal to Fn is less than which is less than or equal to C2 multiply Gn for all n where n is greater than or equal to n0. Actually, Gn provide more precise asymptotic analysis compared with big O and big omega notation. Gn is both an upper bound and low bound of function Fn. Okay? That gives more precise description of the function's growth. Okay? When Fn equals big zeta Gn, in this case, Fn is one of member of function set big zeta Gn. We can summarize the relationship among the three notations. You can see that big zeta is the intersection of big O and big omega. This means a function is in big zeta if it is both in big O and big omega. In other words, if it has both an upper bound and a lower bound defined by the same function gn. Okay, until now, I just explained the definition of asymptotic notation, big O, big omega, and big zeta. Here, we can solve the following equation by using such asymptotic notation. First, we want to show that n squared over 2 minus n over 2 equal big zeta n squared. Here we can find two constant C2 and N0 satisfy this equation. And also, similarly, we can find the constant C1 and N0 double prime satisfying this equation. So it means that we can find C1, C2, and N0 to provide upper bound and lower bound. Okay, this we can find some constant C2 which is always greater than or equal to this expression. Okay, and also we can find another constant C1 and N0 to satisfy that n squared multiply C1 is less than or equal to this expression. Similarly, we can also show n is not in big zeta n squared. In this case, definitely we can easily show this constant C2, but probably it is not possible to find C1 satisfying this relationship. C1 multiply n squared is less than or equal to n. We know that this low bound relationship only holds for n is less than or equal to 1 over C1. So we cannot find a single N0 such that this is true for all larger n. That means that n is not in big zeta n squared. Let's look at more example to understand when a function is not in big zeta. First, we check if 6n cubed is in big zeta n squared. In this case, probably we can show a low bound relationship, but it is not possible to hold upper bound relationship. So focus on the upper bound. 6n cubed is less than or equal to C2 multiply n squared. We divide both sides by n squared. In this case, we get n is 6n is less than or equal to C2. Okay, so in this inequality expression only hold for n is less than or equal to C2 over 6. And also, I want to check whether n is in big zeta of log n. In this case, for the upper bound, n is less than or equal to C2 multiply log n. This gives C2 is greater than or equal to n over log n. But as n gets larger, n over log n also grows without bound. So it is impossible to find C2 that works for all large n. That means n is not in big zeta log n either. It is not possible. Okay, we are now looking at a visual comparison of how fast different functions grow as input size increases. We have the size of input and we have the time to complete an algorithm measured in operation. Each curve in this figure represents a different time complexity. As we move to right, we see that functions like big O1 and big O(n) grow very slowly, while big O(n) cubed and big O2 power n and big O(n) factorial grow very quickly. The green area represents efficient algorithm. They scale well even for large input size. Yellow zone could be acceptable in many practical cases. However, red shows algorithm with poor scalability. They become too slow as input grows. But in real-world situation, we sometimes use big O(n) squared and big O(n) cubed algorithm if the input size is small or the algorithm is not run often. We can classify time complexity into two main categories: polynomial time and exponential time. Polynomial time include functions like big O1, big O log n, big O(n), big O(n) log n, big O(n) squared, and big O(n) cubed. These can be expressed in the form of n raised to a constant power, such as big O(n) squared and big O(n) cubed. Exponential time include functions like big O2 power n or big O(n) factorial, where the input size appears in the exponent. These functions grow much faster as the input increases. The compression shows that big O(n) power k grows slower than big O k power n. That is why exponential time algorithms are usually not efficient for large input size. Okay, at the beginning of this lecture, I explained the first sorting algorithm named insertion sort. We now analyze the time complexity of this insertion sort algorithm in three cases. First, the worst case happens when the input size is sorted in reverse. Each element must be compared with all the previous one. In this case, the time complexity becomes a total cost of big zeta n squared. You can calculate this by using arithmetic series. Next, the average case assume all input order are equally likely. Here about half as many comparisons are needed each time, but this still gives us big zeta n squared over. And also, probably best case, input is already sorted. In this case, only one comparison is needed for each step, so the time complexity becomes big zeta n. So we can analyze the performance of insertion sort algorithm by using asymptotic analysis. Okay, so big zeta n squared is the upper bound of the performance of this algorithm. It guarantees. So is insertion sort fast? Probably for small n it is acceptable, but probably for large n, maybe the learning time becomes grows quickly in the quadratic manner. Okay, probably I want to check whether you fully understand the concept of asymptotic notation. First question is insertion sort big O n squared? Probably you should answer yes. This is true because the time complexity is big zeta of n squared. Okay, we already show worst case time complexity is in big O n squared. How about big O n cubed? Is this true? Maybe some of you think that this is not true because worst case just show big O n squared. Okay? However, you should also answer true. This is also true because big O gives an upper bound. Maybe this is tight, but maybe this is not tight. Okay? Since n squared is smaller than n cubed, this statement still holds. Okay? However, you should remember that big O n squared is the tightest upper bound of the insertion sort algorithm. Okay, thank you for your attention. Do you have any question?